Hi, welcome back. Remember we're talking about Lyapunov functions. And Lyapunov functions are really the simple thing. We had two ways of explaining them. First was the physics way, where there's some minimum value, and you've got a process that, if it changes its value, it moves down every period. So if it's moving down, 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 eventually it's going to stop. It's going to hit the floor. It could stop before the floor, but it's got to stop because of the floor. Or in economics, we often talk about systems where there's a max. And so every period, if the process moves, its value is going up. And since there's a ceiling here, the process has to stop there. So Lyapunov functions give us a way to say for sure that a particular system's going to equilibrium. Now, that's if we can construct one. If we can't construct one, then we don't know. Maybe it goes to equilibrium, maybe it doesn't. What we want to do in this lecture is just remind ourselves of what Lyapunov functions are, and then take an example, take a famous example of a puzzle that's out there, and show how this very, very simple framework helps us make sense of that puzzle. Before we get to the puzzle, though, I first want to just remind ourselves of what a Lyapunov function is. A Lyapunov function is a function f that has a minimum value. We're going to do the minimum case here. And then there's another assumption that it satisfies. If the process moves, if it's not in an equilibrium, then the value of f falls by some amount k, some amount at least k. So what you've got is a process that's got a minimum value, and if it's moving, if it's not in equilibrium, then it has to fall by at least k. So what that's going to mean is eventually you're either going to stop or you're going to hit the floor. And so what that means is you're going to get an equilibrium. Here's the puzzle. Go to any major city, and this is a picture of Stockholm that you see to my right. And what you see is amazing order. Restaurants have the right number of people in them, so do coffee shops. There's not huge line behind dry cleaners. There's traffic, but it's typically not incredibly backed up. And the interesting thing is there's no central planner. It's like the city self-organizes in some way so that there's the right number of people at the right places. We're not all bunched up in particular places, and there's not places that are completely vacant. It's almost as if there was a central planner telling people where to go, but we know there isn't. So how is it that cities have this amazing structure that when you go to the grocery store, they've got the right groceries for you, there's the right number of workers. When you hop on the train, the lines aren't incredibly long. That when you go to the grocery store, when you go to the dry cleaners, it's not incredibly crowded, nor is it particularly empty. What enables the city to self-organize in the way that it does to be so darn efficient? That's the puzzle. And what we're going to see is that Lyapunov functions can give us some inkling as to why even huge cities can self-organize in interesting ways. So here's the idea. Suppose that you've got 5 things you've got to do during the week. You've got to go to the cleaners, the grocery, the deli, the bookstore, and the fish market. So these are 5 things you have to do at some point during the week. You always got to go get fish and books and get your clothes cleaned. So this sort of stuff. And you can choose which day to go. So here's how to think of it. There's 5 days during the week. Assume you take the weekends off and you just read your book and have some fish wearing your nice clean shirt. So there's 5 days, Monday through Friday. And each day you have to decide during your lunch hour where to go. You assume maybe Monday you go to the dry cleaners, right? Tuesday the grocery store, Wednesday's the deli, Thursday's the bookstore, Friday the fish market. This would be just a route that you would take during the week, and somebody else might take a different route. And what we want to see is by people choosing these routes, whether or not the system is going to organize in such a way that you don't get huge crowds at particular locations. So we'll see how we can map a Lyapunov function onto this process. So here's the idea. Suppose you've got 5 people, and each one of these people chooses some random order in which to visit these different locations. So everybody else is just like you. Everybody else has to go to the cleaners, the grocery store, the deli, the bookstore, and the fish market. And they also pick 1 day a week to go to these things. So each person has chosen their route. This may be your route. This may be my route. This may be somebody else's route. Everybody's got their own route. But what we'd like to do is not go to some place that's really crowded. Because if it's really crowded, then we've got to wait in line, and it may take our whole lunch hour and have time for our lunch. So the rule is you're just going to want to sort of avoid crowded places. And what we're going to see is if people follow that rule, then we can put a Lyapunov function on the process and show that it's going to go to an equilibrium and go to a pretty darn good equilibrium. So here's the idea. We're going to assume the following behavior, that people want to avoid crowds. So I pick a route, and if it turns out that I notice, boy, when I go to the cleaners on Monday, it's incredibly crowded, I switch that with another location so that so Monday I go to a place that's less crowded. So I'm just going to switch the time I visit the dry cleaners, maybe the time I visit the fish market, in order to bump into fewer people. That's the rule. And then we're going to see if that's the rule, that this process is actually going to self-organize into something that makes a lot of sense. So again, here's the idea. Everybody's choosing these routes, And let's look at this person here, this first person. The very first day, they're going to the cleaners. But notice there's 3 other people at the cleaners. So that means there's 4 people at the cleaners. What they'd like to do is not have 4 people at the cleaners and have to wait in line. So what they might think of is, like, if I go to the fish market here, there's no one going to the fish market on the first day. So if I switch the fish market with the cleaners, then Monday I won't see anybody at the fish market, and Friday I won't see anybody at the cleaners. So this first person realized, hey, if I just switch these two, then I'm going to run into fewer people. That's the idea. That's the behavior we're going to assume that people follow. What we want to show is we can put a Lyapunov function on this process and show that this system is going to keep going down and eventually has to stop because there's a min. So what's the Lyapunov function? Remember I said this is the hard part and it's hard. So the first thing you might think of is, well, maybe it's just the total number of people at each location. Well, let's try that. So how many people go to the cleaners? Well, 5 people go to the cleaners. How many people go to the deli? 5 people go to the deli. And what you realize is 5 people go to every location. So that's not going to work, right? Because even if I switch my route, there's still 5 people going to the cleaners and 5 people going to the deli and 5 people going to the fish market. So this first attempt of total number of people at each location, not going to work. So let's try something else. Here's another attempt. Let's have it be the total number of people that each person meets. So how many people do I meet in a given week? And now let's look at our example. So we start out here and we look at this person, and right here, and you think, okay, on the first day, they meet 3 people. On the second day, they meet no one, or he meets no one. On the third day, meets 2 people. On the fourth day, on Thursday, 2 people. And on Friday, 1 person. So that's 5, 7, 8. So this person meets 8 people. Well, now let's suppose they switch and go to the fish market on Monday and go to the cleaners on Friday. So this person switches to be less crowded. Well, now on Monday, they meet no one. On Tuesday, they meet no one. On Wednesday, they meet 2 people. On Thursday, they meet 2 people. And on Friday, they meet no one for a total of 4 people. Now remember, before, they met 8. So by switching those 2, they reduced the number of people they meet from 8 to 4. We got to be a little careful here because there's also 4 other people. What about those 4 other people? Could their numbers have changed? Well, they did, right? Because these 4 people, these people that were C here, before we're meeting this person, and now they're not. So in addition to this person running into 4 fewer people, the 4 people they were meeting also run into 4 fewer people. So the total reduction in the number of people that meet each other is 8. It's going to be 4 times 2, which is 8, because each person that person 1 doesn't meet also doesn't meet person 1. So there's a total number of 8 fewer meetings. So this is going to be a Lyapunov function. If people's rule is switch so that I meet fewer people, then when somebody switches, they meet fewer people meet them, so the total number of people who meet each other falls. Now let's ask, is this a Lyapunov function? Well, what are the conditions? The first is, does it have a minimum value? Sure, 0. If nobody meets anybody, then that's the best you could do. So yes, there's a minimum value. It's just 0. Second, if it's the case that somebody changes their route, does it mean that the total number of people that people meet falls? And the answer again there is yes, because if I move, I'm moving so I meet fewer people. It also means that fewer people meet me, which means that the number of people met has to fall. So if anybody moves, the number of people met has to fall. But remember, we also have to have that it has to fall by at least some amount k. Well, in this situation, it's easy. That k is easy because I'm meeting at least 1 fewer person. And if I'm running 1 fewer person, that person's also not meeting me. So k is going to equal 2. If I'm meeting 1 fewer person, then there's 1 fewer person meeting me. So at least 2 people have lowered the number of people they meet. So now I've got a function with a minimum of 0. It goes down by 2 each period. So therefore, the process has to stop. So if I take a route selection process like this and people are switching, what you're eventually going to get is you're going to get that everybody meets no one because you can keep switching. So people are going to keep switching until you would get an efficient ordering of people so that nobody's running into anyone else. Now to prove that this thing only stops at 0 takes a little bit more work. So we won't do that. But what's going to happen is you're going down by 2 each period and it just keeps going down, 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 down until eventually nobody's meeting anybody. this gives us an understanding. It's not a full explanation, but it gives us some intuition as to why when we go to a city, it's so organized. Because people are trying to avoid crowds. If everybody's trying to avoid crowds, then what happens is you get a relatively efficient distribution of people across activities and restaurants and shops and museums and things like that. So the whole city seems to be organized as if by a central planner, when in fact it's self-organizing because of the fact that people are trying to avoid running into too many people, and what you end up getting then is a reasonably smoothly running city without some massive central planning attack, without us getting signals like, it's okay, you can now go to the cafe, Scott. They don't have to tell me that because people are going to develop routines of when they go to particular locations in order to avoid those crowds. This is pretty cool, I think. What have we got? We have a very simple model, right? Simple model is there's a min. If the process moves, it goes down by some amount each time. Therefore, the process has to stop. We use that model to say, let's think about how a city organizes itself. How is it that people in a city choose where to go, and how does it seem to be so efficient? And what we see is that people's maneuvering within the city is probably somewhat to avoid crowds, to go to places you like, but not wait in huge lines. So in doing that, you're always reducing the number of people that you meet. Let me be just a little bit critical of this for a moment. This was an extreme simplification because this model says the city's going to go to an equilibrium with everybody choosing the exact same routes. Now, in fact, a city's more of an open system. There's tourists coming in, there's all sorts of people being born and people dying and new businesses starting and all sorts of things. So that's going to keep a city churning and somewhat complex. But within that process, there's all sorts of people who develop regular routines of places that they go. And those regular routines move the Lyapunov function down, down, down in terms of the number of people that each of us runs into. And allows the system, even though the influx maintains some complexity, to be relatively efficient, to sort of keep down the number of crowds that people run into. So the model doesn't fully explain the city, but what it does is it gives us the insights into how the city is able to organize itself in such a way that there's never too many people at the barbershop and never too many people at the cleaners, and always some people at that cafe. It's never completely empty. All right, thank you.